Hey, this is the next part in a brief series on eigenvalue and inequalities. I'm pretty sure there's going to be 5 or 6, maybe 7 different talks or videos before I post my current research. So we'll jump right in. The Courant Fischer min-max theorem. Here we have a matrix m by m symmetric, ordered eigenvalues. Then for any h 1 through m, we're going to let b of h be an m by h minus 1 matrix, and c of h be an m by m minus h matrix, with the products both equaling the identity matrix with the right dimensions. If those hold, then these inequalities are true. And the approach that we're going to use is we're going to show that this quantity has to be less than or equal to this, and then we're also going to show that it has to be greater than or equal to this. And if it has to fulfill both of those requirements, that means it has to equal it. And then we'll use the same approach here. So first, let's let x of h be the first or they're going to be the eigenvectors associated with the first or the h largest eigenvalues. And then the y sub h is going to be h through m eigenvectors associated with the m minus h smallest eigenvectors, m minus h plus 1. So if we let h or x sub h minus 1 be a matrix of the first h minus 1 eigenvectors, it has this dimensions with and the eigenvectors are going to be orthonormal. So then it has this quantity. This product has the identity matrix. So now, and I initially had a step in here that I thought would help clarify it, but I don't think it does. And then I didn't want to erase everything that I have, so I just whited it out. So here is our original quantity that we want to show is equal to lambda h. But if we look at this in detail, this piece here, the maximum says for every h that satisfies this quantity, or this this requirement, for each of those we take the maximum of this, and then we move to the next matrix that satisfies this and look at the maximum possible, and then we look at the next matrix, and we do this till we find every matrix that satisfies this requirement, find the maximum. So we have a list of all these maximum values. Then we find the minimum of all those that we just found. Okay, so if we take one of these BHs that fits the requirement, then and then we don't look at all the rest, that particular case has to be greater than if we look at all the other possible values and take the minimum. So what we do is we stick this h, because it fits the requirements, in here, and the minimum of that particular value has to be greater than if we were to look at all the BHs that satisfy this requirement and then take the minimum. Now, we could get lucky and it may be the minimum, and that's why the equal sign is there, but in general it has to be greater than. And so what we do is we take this and stick in this x sub h here, and it meets this requirement. And then in lecture part 2, we showed that this maximum is lambda of h. So this quantity has to be greater than lambda h. So now let's show that this quantity has to be greater than lambda h. We showed that it has to be less than or equal to lambda h. So now let's pick an arbitrary BH, which is part of the theorem requirement. So with this BH, it produces an identity matrix X H minus 1. So now let's note that if we take BH prime times H, that this matrix is H minus 1 by H. Okay, so there's more columns than rows. And then that says that this is a singular matrix, which says that we can find a Y of, the column, we can find a Y, the linear combination of columns that equals 0 such that the coefficients are not 0. And what that means is if we take a vector, not 0, that we can take the linear combination of these columns and it equals 0. And that's true because this matrix is singular, meaning the columns are dependent upon one of them, because there's one more column than rows. It has to be. Okay, so now if we look at this quantity, okay, all right, so now let's don't look at the minimum piece, just look at the maximum piece of this. Now this is true for all X having the B that fits this condition, okay? Or, we're not going to look at, but notice here that this BH prime is this, and this can act like our X vector. So if we, instead of looking at every possible H, and then we find the max, do the next one, find the max, do the next one, and then we take the maximum of all those possibilities, that's going to be a big number. But if we just look at one case, not all of them, then that may be the maximum possible value, but it may not be. So there's an equality sign. But if we only look at one and not the rest, then it has to be smaller than the maximum if we look at all of them. So if we stick in one X there, particularly this X, so we're looking at this, dang it, and instead of looking at all possible B's, we pick X's, we pick one, which is this, and we stick that in for X. This quantity has to be smaller than if we were to look at all possible X's and find the max. We're just doing one. Now we may have found the biggest, but probably not. So then if we look at this quantity, take the transpose, and then this piece here is, part of the spectral decomp. It is lambda H, where it has to do with the diagonal of this is the H largest, lambda 1 through lambda H diagonally, and this has to be greater than that smallest eigenvalue in there. And this is also one of the previous lectures, so it has to be greater than the smallest. But one note is that this tends to be true for whatever BH we pick. So we picked an arbitrary BH. So if we take the minimum of this relationship still holds. And so this is true for all BH. So that says that this has to be greater than lambda H. But if it's greater than or equal to lambda H and less than or equal to lambda H, that means it has to be lambda H. Okay, so that is the first part of the theorem. And the second one also follows similarly. Let's let y sub h plus 1 be an m by m minus h matrix, and since they're orthogonal vectors, the product is the identity matrix. And the same sort of relationship here. For any Cn that fits this, we find the minimum. Then we pick the next CH and find the minimum, and then we keep doing it infinitely, so we have like a bunch of these values, and then we take the maximum. That's going to be a big number. So if we just take one possible CH value, and that has to be less than this quantity. So if we plug in this y sub h plus 1 into here, which fits the requirements, then this has to be less than or equal to this. And so finding the minimum of this is lambda h, and that was in a previous video. So then we pick an arbitrary h, ch, that meets this requirements of the theorem, and then we note that if we take if we post multiply it by y sub h, then this has this dimensions, which means that it has one more column than rows, so this has to be a dependent matrix. So we can take a linear combination of the columns and it equals 0 with this y vector not equal to 0. And then the same sort of argument is if we look at just the minimum piece here of this, and then we pick a particular x, then it has to be greater than this. Because if we pick a ch, find the minimum, pick a ch, find this value, pick a ch, find the value, and we take the minimum, and that's has to be less than if we just pick one of those and plug it in. Now we may have found the minimum, but probably not. And so that's what this quantity represents. We're going to put in x, which is this piece here, in for the x. So this has to be greater than that. And then the spectral decomp says it's this, and this has to be less than or equal to lambda h. And because this lambda h is the largest eigenvalue in this diagonal matrix. But this relationship is true for whatever ch we pick. It doesn't matter. So if we maximize this, we still get that this quantity is less than or equal to h. But it can't be greater than or equal to h and less than or equal to h. That means it has to equal h. And that's the proof of this Courant Fischer min-max theorem. Now, one more proof, and I know it's getting long. This will go pretty quickly. This is Weyl's theorem. And this says if we have A and B m by n symmetric matrices, for all h 1 through m, this quantity holds. And this is going to be pretty interesting, that if we want the largest eigenvalue of this, it has to be less than the largest eigenvalue of A plus the largest eigenvalue of B, and vice versa if we want the minimum, and this is true for any h. So let's let B be an m by h1 matrix with the product is the identity matrix. And if we look at this quantity here, we want to find the h largest eigenvalue of this. Then that, on the previous theorem, it says that this quantity is equal to that h largest value. Okay, we just proved that. Now we can do some algebra here and break it up into two pieces. So this is still the same as that, and break it up. But if we look at this quantity and the minimum, now remember there's a restriction on what x can be. It has to, when you pre-multiply it times some bh vector. If we unrestrict this just for this piece here and find the minimum value, the possible minimum value has to be less than the minimum if we restrict it under these conditions. So let's put the minimum, unrestricted minimum, in here. Then we know that this has to be less than this quantity. Okay, and since this is a constant, we can pull it outside this min-max relationship. And then this, we just showed, has to equal the lambda h sub a. That was the previous theorem. and then we bring this down. So this quantity has to be greater than this quantity. And that's half the theorem. And the next theorem is if we let C sub n be any m by m minus h matrix with the product equaling identity matrix, and we want to find the h eigenvalue of a plus b, then from the previous theorem, if we take the max min over this constraint of this quantity, that equals the h largest. Okay, then we can do some linear algebra in here to separate them. And then if we look at this and find the unconstrained maximum, let all x's not equal to 0, then we know that that's the largest eigenvalue of b. But if we constrain it using this, then that has to be maybe smaller than the unconstrained. So what we do is we stick the ith largest eigenvalue of b here. Then since that's a constant, we can bring it out here. And then this, we just proved that that's the h largest eigenvalue of a. Okay, well then we just showed that the proof that this has to be less than or equal to this, and it has to be greater than or equal to this. And that's the results that we wanted to show. Well, I hope you enjoyed it. If you liked it, please like it. And if you don't want to miss the next 2 or 3 videos in this series, please subscribe. Thanks. Bye.